This is our lab introduction for the laboratory for identification of unknown aldehydes and ketones. We're going to use some classic reactions of aldehydes and ketones. These are things that could be used in other types of synthetic reactions, but we're going to use the products of those reactions to identify unknown aldehydes and ketones. Our first reaction is the Tollens reaction. And the Tollens reaction takes advantage of the fact that aldehydes are easily oxidized. And they're easily oxidized to carboxylic acids. Right? Carboxylic acid is our product here. Well, when things are oxidized, something has to be reduced. And in this case, what is going to be reduced is the silver ion. And we're going to end up with silver metal that precipitates on the surface of a clean glass test tube. And so the Tollens reaction is often called the silver mirror reaction. And this was a way at one time that silver was deposited on glass to make high-end mirrors. Now, the Tollens reaction is dependent on the formation in solution of a silver-ammonia complex. So we will start with silver nitrate, which, being a nitrate, if you go back to your solubility table from general chemistry, nitrates, when we put them in water, are soluble, and we would get the silver ion plus the nitrate ion, aqueous. But silver ions, if you remember your solubility chart as well, silver ions precipitate rapidly with a lot of different anions. And so to hold it in solution and to put it in the proper state for reduction, we're going to create a complex with ammonia. If you put silver ion in solution in the presence of ammonia, you get a complex where the neutral ammonia, two molecules of the neutral ammonia, complex with the silver ion, and that complex cation is still soluble in water, but that stabilizes the silver ion to keep it from precipitating with other anions. And so we will use silver nitrate to get our silver ion in solution, and then our silver ion will react with two molecules of ammonia in solution to make our complex silver why is my eraser not working? Anyway, silver ammonia 2, right? Silver ammonia 2, and all that is positively charged. Right there. Okay? So in the reaction, the silver ion acts as a Lewis acid, and the oxygen of the carbonyl of an aldehyde acts as a Lewis base, and we create a complex interaction that makes the oxygen positively charged and makes the carbonyl even more polar, making this carbon a better electrophile. So water in the solution can attack that as a nucleophile, that opens up the carbonyl, and you get this tetrahedral intermediate, this tetrahedral oxonium ion. The tetrahedral oxonium ion is acidic, and with the ammonia in solution, ammonia can act as a base, take the extra hydrogen ion, and then we get this hydroxyl group. In the next step, this hydroxyl group acts as nucleophile, attacks another silver ion. Now we've got two silver ions. Now we have this protonated complex. Ammonia comes in as base, takes the hydrogen ion, and we end up with two silver ions, two oxygen atoms attached to the same tetrahedral carbon center. So now we get to the reduction part. The silver ion has space for one extra electron. So if it takes one electron from this bond, we leave behind a free radical. And what's not shown here is that silver metal is the result, and that precipitates on the surface of the glass. This free radical oxygen can take the hydrogen and its one electron to create a new bond, leaving a free radical in this tertiary position. But this free radical can share its electrons, or its electron. It can take one electron from this bond the silver ion can take the other electron. We get another release of silver metal. Ignore that plus. We get another release of silver metal, and the product then is the carboxylic acid. And so we have oxidized our aldehyde to a carboxylic acid, and in the process we have reduced two silver ions to silver metal. Those precipitate. So if we get a precipitation of silver on our glass, that tells us our starting product was an aldehyde. Okay? So we'll move to the next reaction. Our next reaction is the iodoform reaction. Right? Remember, the haloforms are have formulas 1 hydrogen, carbon, and 3 halogens. So they are the trihalomethanes. So in this case, iodoform is the triiodomethane. And we get these specifically in a reaction of methyl ketones. If we have a methyl group adjacent to a carbonyl group, no matter what this group is here, it can be aromatic, it can be aliphatic, a hydrocarbon, it can even be a hydrogen, which means this could be acetaldehyde. But we're going to focus on methyl ketones, right? So a methyl group next to a carbonyl group, but it can react with all different kinds of carbonyl compounds that have a methyl group next to the carbonyl. Now, this reaction depends on an important property of carbonyl compounds, and that is that the carbon alpha to the carbonyl is more acidic than we would expect for normal carbon-hydrogen bonds. And it's because of the formation of what we call an enolate intermediate. Now, this figure is a little mistaken in that this is not really the enolate. if we look at the alternate resonance form of this, right, the alternate resonance form would be this. The negative charge right there, right? So the unshared pair of electrons left behind after deprotonation, and let me put them right there. The unshared pair of electrons left behind after deprotonation swing here to create a double bond, but to make space for that, the oxygen has to open up and form this alkoxide-like group. And so this is where we get, this looks like if this were protonated, this would be an enol that we talked about before. And so the 8, just like with acid naming, the 8 is designated that our enol is deprotonated, just like we use the 8 in acid naming. So it is that resonance and the sharing of this negative charge between these two atoms that stabilizes this carbanion. And so this reaction is going to take advantage of our ability to create this carbanion stabilized by resonance. And we'll see other reactions that use this carbanion form as well. So in this reaction, our enolate is going to act as a nucleophile and attack an iodine molecule. And that's going to cause almost an SN2 reaction where the other iodine gets kicked off as an iodide ion. And so you end up with an iodomethyl ketone. But now we've created a situation again where there are hydrogens on a carbon next to a carbonyl. Those hydrogens are more acidic than we would expect, and we do it again. Hydroxide ion as base, takes hydrogen ion, leaves unshared pair of electrons. The whole thing is stabilized by resonance to another enolate. The carbanion form acts as nucleophile, kicks off iodide ion, and now we have a diiodomethyl ketone. And lo and behold, we do it again. Hydroxide ion acts as base, deprotonates, creates a carbanion with an unshared pair that can act as a nucleophile, attacking the iodide ion, or an iodine molecule, releasing an iodide ion, and now we have a triiodomethyl ketone. Now at this stage we're out of hydrogen ions, so we can no longer deprotonate this, and now we get an interesting other reaction. What's going to happen here is our hydroxide ion acting as a nucleophile will directly attack the carbonyl, and that will tend to open up our carbonyl with the unshared pair going to the oxygen, and something in here, probably a hydrogen ion from water, will protonate that. So you end up with this where'd it go? With this ketone hydrate form. So we get a triiodomethyl ketone hydrate. And that triiodomethyl ketone hydrate is in some ways unstable. And it's helped by the fact that these iodines are electronegative and pull electron density away from this carbon, which is pulling on these electrons and stabilizing it. So if we have something that can accept that hydrogen ion, like water, so if water can accept that hydrogen ion, then these pair of electrons can swing back in to form a carbonyl, but we need a leaving group. And so it is this triiodomethyl group that acts as a leaving group. Right? There's our electrons, there's our carbon, there's our three iodines. And so we get a carbanion stabilized by the large size of these iodines and its electron withdrawing capabilities. And so then, right, this is our iodoform, right? This is this. I think the carbon just isn't showing here, right? This is our iodoform. It can react with water. It can be protonated, and you end up with iodoform, right? Right? I'm sorry. That's our Ci3 minus, right? That is our triiodomethyl anion. It deprotonates water, and we get iodoform as our product, and iodoform precipitates. And it is a light yellow color. So if you do this reaction and you get a light yellow precipitate, that is a presumptive test that says I started out with a methyl ketone. So synthetically, this reaction is a way to make a carboxylic acid out of a methyl ketone to remove the methyl group. But it is also a test that we can use for the presence of a methyl ketone in a sample. Okay? So we'll move on to the next reaction. Our next reaction is based around an amine acting as a nucleophile to attack the carbonyl of any aldehyde or ketone, right? So R and R1 can be aromatic or aliphatic groups, or they can be hydrogens. Any aldehyde or ketone will react with this compound 2,4-dinitrophenylhydrazine. So hydrazine is this nitrogen-nitrogen compound that is very reactive, but we're putting a dinitrophenyl group on the hydrazine. So carbonyls are very polar, right? Oxygen pulls electrons that way. So the nitrogen of an amine, and in this case the amine is part of hydrazine, can attack and open up to form a tetrahedral intermediate, right? So here is our tetrahedral intermediate. Our nitrogen is now positive. Our oxygen is negative, right? In our solution, right, we have water, and so the oxygen is protonated by water. The nitrogen is deprotonated by water. So we get this neutral, this neutral form with a nitrogen and a hydroxyl all on this tetrahedral carbon. Now, as the reaction continues, right, if we reprotonate our hydroxyl group, then we can get a reaction where the nitrogen, once we protonate that hydroxyl group, we get this, and we get water as a leaving group. If water tries to leave, right, then the nitrogen can give its unshared pair of electrons to this carbon to replace the leaving electrons, and we get a C double bond N, what we call an imine group, that replaces our carbonyl group, right? And so this reaction of aldehydes or ketones to form imines is a common reaction. And so in this case, what's interesting about this imine, if we go ahead and put electrons here, right, based on this structure, if we look through, all of these atoms are aromatic and sp2. These nitrogens are sp2. Even though this looks like it has 4 areas of electron density, again, we have 2 atoms, or we have an atom with an unshared pair next to an sp2 hybridized atom. So that nitrogen is also sp2. That nitrogen is sp2. And that carbon is sp2. So we've created a long and extended sp2 conjugated system all the way through the nitrogens around the ring and to these nitro groups. And what we find is, if we go back to our UV visible spectroscopy, the length of a pi system, right, the longer the pi system, and there was even a question about this on a test first semester, the longer a pi system, the longer the wavelength of light it absorbs, and the lower the energy. And we can get this energy into the visible spectrum. Now, as we see it here, this is all the same, right? But what happens is the length of the pi system depends on whether there are any pi bonds in either of these groups. So if there are no pi bonds in either of these groups, then these derivatives appear mostly yellow. If there are a couple of pi bonds in there, in our alkyl groups, these can appear orange. But if we have a long conjugated system, like say an aromatic system, that lowers the energy of absorbance even more, and these turn red. And so the color of the derivative can help tell us something about the structure of the groups on our original aldehyde or ketone. The other thing we can do is these things are solids. And so as solids, they have characteristic melting points. So we can determine the melting point, and there are tables relating alkyl group structure to the melting point. So we can learn something about the structure from the color of the derivative, but we can learn something else by the melting point of the derivative. And so the 2,4-dinitrophenylhydrazine test is an important test for determining things about the structure of aldehydes and ketones, as well as reviewing the important chemistry of imine formation, which we see a lot in organic chemistry as a mechanism, and I've seen it in some of your papers, we encounter that structure a lot in biochemistry. So this reaction is important in and of itself, and it is important as a qualitative chemical test. And so here are the notes that Dr. Stickney had made up before. This is only covering toluenes and iodoform. It's not covering, here it is. Here's the 2,4-dinitrophenylhydrazine test, right? This is old book, so we don't have to worry about these pages, but you can look in the index of Jones to look for the formation of imine derivatives and 2,4-DNP derivatives. So this is another layout of the mechanism based on Dr. Stickney's previous notes that can help you prepare your pre-lab. These reactions are very straightforward. They're going to be done in small quantities in test tubes. We're not going to need our complex synthetic glassware for these. These are just basic chemical tests. So I hope this will help you put together your pre-lab. If you have any questions, I hope you can get with me Monday morning. Good luck. Thank you.